Hello everyone, my name is Ali Reza Azadbakh from Computer and Data Science Department of Şehit University. In this presentation, I'm going to propose a novel deep learning model based on visual transformer for the task of license plate optical character recognition. Optical character recognition of the license plate is a crucial task used in traffic management, vehicle tracking, car ticketing, and parking management in modern cities. Developing an OCR system is not a simple task, and the system should be robust to many factors, such as blurry images, poor lighting conditions, variability of license plate colors and special characters, physical impacts, possible frauds, and the weather conditions. A robust OCR system needs to cope with the various environments while maintaining a high level of accuracy. In other words, the system should work well in natural conditions. As the field of computer vision grows and advanced deep learning architectures are introduced, the accuracy and confidence of deep learning models for tasks like image classification, object detection, and text recognition are improving daily. However, the downside of these advances is that deep learning models usually need advanced computation resources and memory units to perform inference in real time. They cannot be implemented on small chips such as Raspberry Pi hardwares. These limitations prevent the companies and researchers from using the full potential of state-of-the-art deep learning models in practice. Due to the lack of rich, large-scale license plate datasets, we first built the LicenseNet dataset, which is a rich and larger-scale license plate dataset consisting of 1.3 million images. After that, we focus on training a small ViT model on a large number of data points and exploit the permutation invariance properties of this architecture to account for various problems in captured license plate images, such as the different angle of license plates in images and deformation and frauds in images that CNN models initially have difficulties in addressing. And in the meantime, we keep the model lightweight, so we could use this model on edge devices with limited computation power. We propose MultiPath with OCR, a lightweight model based on visual transformer. Our proposed model has 3 times fewer trainable parameters than previously proposed CNN-based models, and it achieves 77% accuracy on the LicenseNet testset. For comparison, we chose convolutional recurrent neural network (CRNN) models and trained it on 2 subsets of LicenseNet datasets. The CRNN model is extensively used in industrial use cases. Even today, this architecture is used as a solution to many vision tasks that tend to extract information from images in an iterative manner, like extracting text from natural images and OCR of scanned documents. In this paper, we aim to propose a lightweight model for Persian license plate OCR, suitable for edge devices with limited computation power. Visual Transformer, or ViT, is a novel deep learning model in the computer vision research community. The transformer architecture was initially introduced in natural language processing. After achieving competitive results in comparison with previous models like RNNs, it gains much attention in the research community. After introduction of a novel model based on transformer for computer vision and achieving a state-of-the-art accuracy in many vision tasks and larger scale datasets, many researchers tend to work on this model to find the capability of transformers and self-attention mechanisms in computer vision tasks. The ViT model is a simpler variation of transformer that only uses encoder modules and one multilayer perceptron on top of a stack of encoders. This model uses the power of the self-attention mechanism to replicate some properties like translational invariance of CNNs. The self-attention mechanism in ViT architecture handles translation and permutation invariance in images and helps the final layer multi-layer perceptron to have an even better and more accurate view of the input image. It's worth mentioning that the full potential of ViT unlocks with large-scale datasets. MultiPath ViT OCR, like standard ViT, consists of two modules. First, a stack of transformers encoders try to extract rich features from patches of the input image. And second, on the top of the encoder modules, a multipath module with n number of multi-layer perceptron with a different number of layers try to perform a classification task of finding each character of license plate. N is the number of characters in a standard license plate. In a standard license plate, Persian license plate, there are 8 characters, 7 digits and 1 Persian character. Our model has 8 paths on top of a encoder's stack. In order to bypass the iterative generation of characters and avoid recurrent layer, each path in the multipath module is responsible for recognizing one specific position of the character in the license plate. For example, the third character in Persian license plate has 26 distinct Persian characters. So, the third path of the multipath module does the task of classification on 26 possible characters. In other words, the last layer of the multi-layer perceptron has 26 neurons. Each path computes its classification loss, and summation of each path's loss backpropagates on the whole network. This study aims to train a lightweight OCR. Naturally, ViTs are data-hungry models. Official and most computer vision benchmarks, like the ImageNet dataset, have approximately 1 million images in them. Due to the lack of a rich and larger-scale license plate dataset, we gather a rich and larger-scale Persian license plate dataset. We collect and annotate 1.3 million license plate images. As of our knowledge, there is only one publicly available dataset for Persian license plate that only consists of 83,000 images. Unfortunately, this dataset has many biases toward natural conditions and the distribution of characters in different positions of the license plate number. Training an OCR model on this dataset does not give good practice and industrial usage accuracy. LicenseNet dataset is approximately 16 times larger than other datasets. Because of the large number of data points, it is applicable for training novel models like ViTs or developing robust, powerful OCR models without biases to characters and natural conditions. In order to create an unbiased dataset, images in the LicenseNet dataset were captured with various cameras from different brands in different conditions like night or day, different weathers, and different shooting angles. Initially, we gathered and annotated around 13 million images, and after that we carefully chose 1.3 million so that any position of character has a uniform distribution. And also, day and night images are the same, and we would have various license plate angles in the datasets. We used an OCR system in cameras to collect our datasets. So as a baseline, we use the accuracy of these embedded models. For comparison with CNN-based models, we tested a CRNN model on the LicenseNet dataset. The CRNN model consists of 7 CNN layers and 2 bidirectional RNN layers, and the whole model trains with CTC loss with standard training settings. As we can see, the 100K subset multipath ViT has a competitive result, and on the whole dataset with a tiny number of parameters, it gained better performance. CRNN and multipath ViT models achieve better accuracy than the camera's embedded OCR. On the full LicenseNet dataset, multipath ViT outperforms its CRNN counterparts with a margin of 2% accuracy. In the meantime, multipath ViT is 3 times smaller than the CRNN model in trainable parameters. So not only multipath has better accuracy, but also it is much easier to train and employ on edge devices and small kits. We showed that with a large number of training datasets, we could achieve a competitive result in the license plate OCR challenge compared to the previous popular models with a lightweight and a tiny number of parameters. It is worth mentioning that the CRNN model was initially trained on a small subset of the dataset consisting of 100K data points. However, the computation limitation made it impossible to train this model with the whole dataset on Google Colab GPUs. So we train it on a more powerful server. Therefore, applying visual transformer architecture in edge devices or computation-limited situation is helpful to keep the model lightweight when we have a large amount of training data.